So our topic today deals with the concept of solutions, and solutions are probably the most iconic image that you can think of what represents chemistry, these mysterious mixtures inside of flasks. And we're going to take this idea apart into a lot of different pieces today and make sure we can understand it. And by understanding solutions, it sets a background for being able to understand a lot of chemical reactions. So we're going to have some learning outcomes today of defining what solutions are and identifying their components. We're going to use a term called molarity to define amounts of components in solutions. We're going to talk about how to dilute a solution if you have one that's too concentrated. And then we'll use solutions to do some stoichiometry problems. And the most classical solution stoichiometry problem is called a titration. So we'll define what that is and start to get some practice solving those kinds of problems. So let's first start with what a solution is. You've probably made solutions many times in your life. You've probably mixed some salt in the water, and when you do, the salt sort of seems to disappear, or it might look like it's become part of the liquid. It hasn't become part of the liquid, it's dissolved and formed a homogeneous mixture. And the way you can tell the salt is still there is that you could boil off or evaporate the water and recover all the salt. So in that case, the mixture is really two components, even though when the salt is all dissolved, it still looks like just one component. So what are the components of a mixture? You must always have a solute and a solvent to make your homogeneous mixture called a solution. So what is a solute and a solvent? The component of the solution that changes its state is the solute, and it's also typically there in lesser quantities. The thing that's there in greater quantities and the thing that keeps its state is typically the solvent. So an example would be if you took copper sulfate, the solute, and you put it in a beaker with water, the solvent is the water, and once the solute is completely dissolved and formed a homogeneous solution, the solid has completely disappeared. All the copper is still there, all the sulfate is still there, all the water is still there, but it's just dispersed throughout the solution and made a homogeneous mixture. So those are the components of a solution. Now there's sort of a couple of ways to classify solutions in a qualitative sort of way. If the amount of solute is very, very small compared to the solvent, then we would say the solution is very dilute. However, if the amount of solute is very large, then we would say it's more concentrated. So you can get an idea of the scale we're talking about. If you put a little tiny bit of red dye into a cup, it would be a dilute solution. If you put a lot of red dye into a cup, it would be concentrated. And there's a sort of a spectrum of concentrations you could get to in between. So just saying whether something's dilute or concentrated isn't quite enough information. It's more helpful if we can be quantitative about it. So what are some ways we can be quantitative describing just how much solute is in a given solvent? What we're going to do is define a concentration, a specific amount of solute in a given amount of solution. And you've probably had a lot of experience. Every time you've looked at a nutrition label for a beverage, you're seeing a bunch of different solutes. For example, this is the label from some Gatorade Pro Series beverage. And here are solutes. It's got sugars, it's got potassium, it's got sodium, a lot of different solutes. And the amounts of solutes are listed on here as grams or in milligrams. But the amount of grams or milligrams is per ounce of solution, since this can comes in ounces. So this type of unit would be, this type of concentration would be grams per ounce of solution. Now, if you're like me, ounces are not the most convenient unit of volume, so a more convenient unit for a chemist would be liters. And that's the type of unit you see for concentration for things like pharmaceuticals, where this is an example of a pharmaceutical for a veterinarian clinic, and it has units of grams per liter in its concentration unit. So grams per liter is a little bit better, but you remember as we're doing stoichiometry problems, it's much easier to work with moles, because then we can see how many moles of one reactant combine with moles of another. So grams per liter is a fine concentration unit, but wouldn't it be better if we had a concentration unit with moles? And for most of the chemistry problems we use, we'll use exactly that idea. We're going to use a concentration unit called molarity, and it's symbolized by a big uppercase M. And it's defined like this. It's defined of the moles of solute, and that's the thing that's present in lesser quantities, divided by the total volume of the entire solution with units of liters. And if we use molarity, then we can solve stoichiometry problems really much more simply than if we use things like grams per liter or parts per million, which is grams per million grams. So let's stick to molarity. That's a much simpler unit for us to use. Let's try a simple molarity problem. Let us suppose we're asked to calculate the molarity of a solution that has 1.54 moles of potassium sulfate, that's the solute, in 125 milliliters of a solution. So where are we going to start? Well, first we should try to remember what molarity is. So write yourself an equation for molarity, and hopefully what you're writing down is that molarity is the moles of the solute divided by the volume of the solution in liters. So what in this equation do we have and what do we need? We have 1.54 moles of solute. We could put that in the top. Next we need the volume of the solution in liters. What do we have? We have volume in milliliters, so we're going to have to convert that from milliliters to liters. So if I do that, I'll just plug in moles on top, and this is liters on bottom. 125 milliliters is 0.125 liters, and I'll get an answer that looks like this. So this is about as simple a problem as you could come across. These problems can get much more complicated, so let's look at one that's maybe a little trickier. Let's talk about a solute, caffeine. Caffeine is found in a lot of beverages, including green tea and coffee. It's a stimulant. It's used to increase mental alertness or wakefulness if you're tired. So what question might you see about caffeine? If an 8-ounce cup of green tea has about 35 milligrams of caffeine, and here's the molar mass of caffeine for you, what is the concentration of the caffeine with molar units? And there's a hint here for conversion if you don't remember ounces to milliliters, which of course I don't. I had to look it up. 1 ounce is this many milliliters, 29.574. So where are we going to start this? Let's start with trying to remember what molarity is. Molarity is moles per liter, so we're going to have to start by converting our ounces to liters. Now, I don't know a conversion directly to go from ounces to liters, but I do have a conversion from ounces to milliliters, so let's start with that. Let's multiply ounces by something that cancels ounces and gives us milliliters. So our ounces will be divided out and we'll have units of milliliters. That's a great step, but we're not done with the volume unit yet. We have to go one more step. Molar units have a liter factor in there, so we need to multiply by a conversion factor to go from milliliters to liters. And when we do that, here's the volume of your green tea, 0.2366 liters. Okay, so now we've got the volume part under control. What's the other part? Molarity is moles per liter. We've got liters, we're going to need moles. So let's go back up to our problem. We had 35 milligrams of our caffeine solute. So let's start with that. 35 milligrams of our caffeine. You've got to go from milligrams to moles. Now I don't have a milligrams to moles conversion, but I do have this molar mass. And that molar mass has units grams per mole. So let's multiply by this factor that converts milligrams to grams. And then we can use our molar mass to go from grams to moles. So let's plug that into our calculator. 35 times 1 divided by 1,000 times 1 divided by 194.19. And I get this number of moles. Okay, so now we have our two pieces of the puzzle that we're going to need. The moles and the liters, so let's plug that in for molarity. Molarity is going to be the moles on top divided by the liters on bottom. And here's your caffeine concentration in your green tea. So that is a trickier problem, and it's important to get some practice with these. And once you've got some practice with it, we can talk about the actual nuts and bolts of making one of these solutions. if you go into a lab, of course you don't measure out your solute in moles. You're going to use a mass balance and measure it in grams. So you measure out your grams, and then you need some way of very precisely measuring the volume. If you need to know the volume with a high level of precision, you're going to have to pick your glassware very carefully. So let's look at the glassware options. There's beakers, Erlenmeyer flasks, graduated cylinders, graduated pipettes, and volumetric pipettes and volumetric flasks. So let's take these apart and see what each one is good for and which one will be a good choice as you're making your solutions. If you were to need some volume of a solution, but you didn't really need to be very precise about how much you had, a beaker or a flask is a good option. It has these graduated markings that give you sort of a ballpark idea of how much you have, but it's not intended to be very precise. So you would store a little bit of water in here while you're in the middle of your experiment, but you wouldn't use these markings to measure it very carefully. To measure something a little more carefully, you could use a graduated cylinder, and that could tell you the volume to maybe 0.1 milliliters or so. But that's not a very high level of precision. If you want to know very, very precisely just how much of a volume you have, you need to use one of these two things, a volumetric pipette or a volumetric flask. So what are the differences between these two things? The pipettes, both the volumetric one and the graduated one, sort of look like a straw, and these are meant to suck up a little bit of solution and then transfer it from one container to another. So this isn't meant to store it, this isn't meant to make your final solution, this is meant to be a transferring agent. So if you use a graduated pipette, you'll have a pretty good idea from these graduated markings, but still a higher level of precision for transferring volumes is this volumetric pipette. Now to make your actual solution, what you would do is you'd weigh out your sample and put it into one of these things, a volumetric flask. You would dissolve your sample in your solvent and then fill the solvent up to this tiny mark here, and that once you've got the bottom of the meniscus right at that tiny mark, you would know exactly, very exactly, what volume you have. And what do I mean exactly? A flask like this is usually known to hundredths of a milliliter. That's a pretty good level of precision with a volumetric flask. A beaker will be of no help at all. You'll really need some specialized equipment like this. So that's how to make a solution. And I'll post a link to a video on our video page so that you can watch this in live action instead of just seeing a description of it. Okay, so what happens if you make your solution and it's a little more concentrated than you'd like it to be? What can you do then? Well, you can dilute the solution. So let me show you how the process of that would work. Let's say you make this flask of dark blue colored solution on the right, and it's too concentrated. You need something that's not quite so concentrated. So you'd use this volumetric pipette to draw some solution up inside it, and this is marked 25, so you can draw up 25 milliliters very precisely. And then you would dispense that volume into a second flask. And after you've put that 25 milliliters in, you'd fill it up to the mark with some more solvent, and what you'd have in the end is a more dilute solution. Now, if you knew the concentration of the very concentrated solution, the dark blue one at the beginning, you ought to be able to figure out the concentration of the light blue one at the end if you knew how much you added to this flask, which we do. We use this 25 milliliter volumetric pipette, so we know how much we put in. And if we know the final volume we end up with, we ought to be able to figure out our new concentration. So what equation will we need to do that? The equation here allows you to figure out your new molarity if you knew the starting concentrated molarity, the volume you took out inside your pipette, and the volume that you diluted it to in the end. So this M1V1 equals M2V2 is a very helpful and powerful equation to figure out new concentrations. So let's see an example of what that might look like. Let's say you have 50 milliliters of a 0.4 molar salt solution. So you take that 50 milliliters and dilute it to 1,000 milliliters. What is the new concentration that you've prepared? What's the dilute concentration? So what we're going to need to start with is look at all the different pieces that we're given. We were given a starting concentration, 0.4 molar. We were given a starting volume, 50 milliliters. What else were we given? We were given an ending volume, 1,000 milliliters, and what are we asked for? We're being asked for the molarity. So we know 3 parts in our 4-part equation, and our 4-part equation is m1v1 equals m2v2. We can know any 3 of these things to solve for the 4th. So let's start plugging in numbers. M1 is 0.4, V1 is 50, and V2 is 1,000. So that's what my equation looks like. And now I just need to algebraically rearrange it and solve for M2. Rearranged, I can plug in 0.4 times 50 divided by 1,000, and I'll get a molarity of 0.02. Now, a couple questions often come up at this point. One is, what units of volume do you need to use? Here we used milliliters. Should they always be liters? Could you use something else? And the answer is this. If you have the same units for volume 1 and volume 2, you can use any volume units you want. They must, however, be the same. You couldn't use milliliters for V1 and liters for V2. You'd have to convert both to either milliliters or both to liters. And hopefully that clarifies it. To do some chemistry, most often what you're doing is chemistry in solution. You're probably going to be mixing a solution A with a solution B to make some new product. And this field of solutions, stoichiometry, allows us to figure out how much of solution A to add with solution B, or if we measure how much of solution A was needed, we could figure out the concentration of solution B. So the ways to ask stoichiometry questions when you have solutions look like this. How much of solution A, this yellow one, was required to react with solution B? Or you could say, what was the concentration of solution A if we measured the volume of solution B that was required? Now, the most classical realization of this concept is called a titration. And that's a way to exactly react 2 different reactants and measure the concentration of one of them. Now, this is often done with acids and bases. So an example would be you put an acid in a flask like this, and you want to know its concentration. Let's say you don't know just how much acid was in this. What you could do is put a known concentration of a base inside this instrument called a burette, and a burette has very nice and precise graduated markings on it. So you could start adding some of this base to the acid, and when all of the acid has completely reacted, you could measure how much you started with in the burette of the base and how much you ended with, and figure out how much was required. So let me show you sort of a simulation of that. In this simulation, the base is in the flask and the acid is in the burette, and you start adding the acid dropwise. So what you'll see as I start this is that the thing that's reacting in here is the OH. So this graph over here shows the starting concentration of OH, and as the acid gets added to it, this OH will start to go down. And we'll know the reaction is done when all of this OH, which is called hydroxide, when all of it has been completely reacted and has gone away. So we'll start the simulation and start dripping our acid in to the flask, and you'll see that hydroxide concentration getting lower and lower and lower. And at the moment that it's reached its lowest point, then the titration is done. So that's an example of what we're talking about with titrations. I'll post another video shortly on how to do the actual acid-base titrations, showing you how to do it in a lab. But in theory, here's how you can solve a titration problem. Let's say we take 20 milliliters of sulfuric acid and we don't know its concentration. So we titrate it with a potassium hydroxide solution with a known concentration. It's 0.1 molar and it's known. and our titration required a large volume, 46.02 milliliters of this potassium hydroxide. And this is the amount that was required to completely react all of the sulfuric acid. The question we can answer is, what is the concentration of the sulfuric acid? And we're going to need the balanced chemical equation to answer that. So when all of the sulfuric acid has reacted, we're using that 1 mole of sulfuric acid reacts with 2 moles of potassium hydroxide, that stoichiometric relationship. So where are we going to start? I think it's helpful to start with writing down what we were given in this problem. So let's start with that. Let's look at the potassium hydroxide. What were we given? We were given a volume that was required to react, and we were given a molarity. What about the sulfuric acid? For that, we were given a volume, but we were not given a molarity. That's what we're intended to find. So how on earth can we find molarity for this thing? Well, if we know that 2 moles of potassium hydroxide react with 1 mole of sulfuric acid, then we can use that mole ratio to get moles of sulfuric acid. And once we have moles of sulfuric acid and knowing the volume, we can get molarity. So our very first task is to convert everything that we possibly can into moles. Now you've got a volume of KOH and a molarity of KOH. Can you get moles? Well, if you remember, as we're trying to do this, that the molarity is the moles per liter, can we solve for moles if we know molarity? Up here that's 0.1, and we know volume, 46.02 milliliters. The answer is absolutely yes. We can find moles if we know molarity in liters. So let's start there. 0.1 molar, that's our concentration. I've taken that 46.02 and converted it from milliliters to liters. And once we've got that, we can just solve for moles. So 0.1 times 0.046. This is the moles of potassium hydroxide in the reaction. So now, what are we trying to do? Let's remind ourselves. We're trying to figure out the moles of sulfuric acid, and right now we have moles of potassium hydroxide. So to get to moles of sulfuric acid, we're going to need this relationship, the 2-to-1 ratio, from the balanced equation. We reacted 4.6 times 10 to the negative 3 moles of potassium hydroxide. Let's times it by something that cancels moles of potassium hydroxide and gives us moles of sulfuric acid. Where are we going to get these numbers? Let's look back up at the balanced equation. 1 sulfuric acid for every 2 potassium hydroxides. We can put 1 sulfuric acid for every 2 potassium hydroxides, and we get the moles of sulfuric acid. Now, we've done a lot of steps. We've got one more to do, because now we have moles of sulfuric acid, we have volume of sulfuric acid, and we're trying to get molarity. So molarity is the moles per liter. We've got moles here, 2.3 times 10 to the negative 3. We've got liters, that comes from the volume up here. And we can just do a little bit of simple math to get the molarity of the sulfuric acid. And that's really the type of information you get from a titration problem, or more generally a solution stoichiometry problem. So I really recommend getting some practice with these so you can get comfortable with them.